Good morning, yeah, it's the morning. Good morning, everybody, and welcome. I don't know when this class starts. Good morning, everybody, and welcome back to Galois Theory. How are y'all doing today?
Good.
How are you doing today, Lydia? That's great. Glad to hear. All right, plan for today. We're gonna take on minimal polynomials again from the opposite approach of how we've done it the last couple of classes. Holy cannoli. With that in mind, I've got my usual office hours this afternoon, 1 to 2. Usual office hours tomorrow morning at 11. And on Monday at 11 and 1. Exam, it's up. It's on Canvas. Check it out. It's due next Thursday. And don't worry, it's only 5 problems.
Oh no. Oh.
I know, it's hilarious.
No.
Right? But yeah, if you haven't seen it yet, there's a couple proofs that aren't that bad. There's a few compute some minimal polynomials of particular element field extension. Here's an integer polynomial proof that it's irreducible. One of those prove this thing is not a PID. A lot of which, the last several of which are all things that you've had to do on the homeworks already. So homework review computation stuff and a couple new proofs just for fun. Sound good? Groovy. Okay, so that's due next Thursday in class. As a reminder, you can work with one partner of your choice. If anybody would like help finding a partner, let me know, and I will be happy to play matchmaker for you. That includes you, Lydia. So, yeah, keep that in mind. Just send me an email if you want some help. And as always, you can come in and ask me questions, and I'll be some amount of helpful. Any questions, comments, concerns? So, Cannibal decides he's feeling hungry and goes out, decides he needs to go out and get some dinner one night. So he goes to the local butcher shop, goes up to the butcher and says, hey, I'm looking to buy some brains for dinner. Butcher says, yeah, sure. I've got a mathematician brain for $1 a pound, engineer brain for $2 a pound, and politician brain for $10 a pound. Cannibal's surprised by this. Says, wait, why is politician brain 10 times as expensive as mathematician brain? Is the quality that much better? Butcher laughs and says, of course not. Just that it takes 10 times as many politicians to get that pound of brain. Haha, political jokes and cannibalism.
I heard a different version of basically the same thing, where instead the joke was that they never used it.
Oh, yeah. It's a rare ingredient that's impossible to find. Yeah, that works too. All right, so back to minimal polynomial stuff. So last couple classes, we've been approaching minimal polynomials from the perspective of, hey, we have some element in some field, and we're looking at a field extension. Let's find the minimal polynomial for that element in the extension. So like if I gave you I, find the minimal polynomial of I over the reals, or find the minimal polynomial of square root of pi over the reals. Today we're going to do something a little different. So what I'm going to do today is I'm going to give you all an irreducible polynomial. And we're going to have to try and find what is an element in some extension for which this is the minimal polynomial.
Whoa.
So instead of starting with the element and finding the polynomial, we're going to start the polynomial, and we need to find the element.
That's crazy.
Whoa.
And with that, here's our next packet today. Hi, Seamus.
Oh.
Seamus, that's yours.
Oh, we need another one.
Why did I give someone?
You just
You
chucked
threw it,
Seamus
you
in the
chucked it at
burger and
me.
didn't give back you.
Oh, I thought I gave. Oh, Matthew, sorry, I thought I gave you.
This is what happens when
Does
you're.
anyone want this one so Dr. Gershel can have to hand another one back?
It's like a paper delivery boy.
With the paper boy, you mean?
Lydia, I'll set yours aside. All right, so let's look at a couple examples to start things off. Let's say we're starting with polynomial f of x equals x squared plus 1. And our goal is to find some extension L over the rationals in some element alpha, an element in L, for which this is the minimal polynomial. So, what would be an extension of rationals and some element in that extension for which x squared plus 1 is the minimal polynomial?
I square root of 2.
What's your field? What's
I
your L?
square, or I just meant I.
Yeah, I'm not interested in you. What? Give me a field.
Oh, Q adjoin I.
I was going to go with complex numbers, but that works too.
Wait, isn't L cubed?
Is it what?
No.
L is the extension
L
of
is
Q.
Over, yeah. Oh, okay, yeah.
And what's your alpha?
I.
There you go. There, given this polynomial, here is a field extension of Q and an element in that field extension for which f of x turns out to be the minimal polynomial.
That was easy.
Oh, okay. How about the next one?
I don't
F
know.
of x equals x cubed minus x squared.
That is reduced.
It's reducible?
In,
X,
oh,
that
but,
doesn't necessarily.
but maybe not in,
Yeah.
oh, shoot.
Yeah, this thing is definitely not irreducible in Q.
No.
Is there a field extension of Q over which this is irreducible?
You could like just always
R.
R.
What?
Yeah, it's
R.
R.
No?
Isn't it?
It's not irreducible.
It's not irreducible in any extension of Q?
It's not like irreducible. Oh, it shouldn't be an extension. It's irreducible.
Yeah, if it's reducible in Q, it has to be reducible in anything containing Q.
That's very reducible.
So it turns out this one is a trick question.
Oh,
It's not the minimal polynomial of anything.
oh my gosh.
Reason being, g of x is reducible in Q. Hence in any extension. Meaning it can't be the minimal polynomial of anything. Because part of being minimal polynomial is that you have to be irreducible. Oops. How about that? All right, Parker, here's one for you.
Yeah, I'm ready.
H of x equals x to the 9
I'm not ready.
minus 8x to the 7 plus 12x to the 6 minus 50.
It's irreducible.
Obviously it's irreducible.
How do you know it's irreducible?
Because they do look like that.
Oh, okay, because people don't think it be like it is. Okay, Emily Rose, how do we know that's irreducible?
Because 2 divides 8, 12, and 50, and 4 doesn't divide 50, and I can't remember the name of that theorem right now.
Eisenstein's criterion, yeah. So we know this is irreducible over Q. Boy, I hope you remember that by the time you take your exam. I mean, Eisenstein's criterion is not on the exam. I mean, yeah, Eisenstein, P equals 2. This thing has to be irreducible over Q.
Are you tricking us?
So it doesn't have the same problem that g of x here has. All right, Parker, I'm waiting. What's your field extension? What's your alpha?
Field extension, I'm gonna say, I would say
The real numbers? That doesn't sound confident, so I'm going to put a question mark down.
It wasn't confident.
We just applied the Monic formula.
The nonic formula.
Oh yeah, it's the whole thing.
Oh, that sounds like a thing I don't know about.
I'm sorry, what? Nonic formula?
Yanni. Yanni. How about this? Let's put something down at least we can feel somewhat good about.
I feel good about that.
Because we know this thing has to have factor into linear terms over the complex numbers.
So if we think about things with non, and we think about a nonagon in the complex plane.
Where are you?
Ninth roots of
So,
I, yes.
I know where he's
So
going
the
with
point
this.
is, you have to get something that'll loop around at degree 9, right? You need it to be, you can raise it to everything, and then when you do it to the 9th power, it goes.
Something involving ninth roots of unity?
Yes.
Yeah.
Yeah.
This is Galois theory.
96 or
So actually finding an alpha is pretty hard.
Yeah.
This thing is turns out this thing is guaranteed to have a field extension and have something over which it's the minimal polynomial for something. Actually finding the something is kind of hard. Nonetheless, we're gonna do it.
Oh,
Y'all ready for this?
you wanted me to do this in my brain. Oh, shucks.
Ooh.
The quaternions are in a field.
There's your L right there.
No.
And here's your alpha.
What the dog? Oh, shoot.
But why?
What?
But it wouldn't be C, would it?
What?
What?
Or-
Oh yeah, well that get rid of that. There you go. There's your field extension.
Can we let that?
There's your
stay-
alpha.
Can we let that stay the answer?
Yeah.
Okay, cool.
Can you just remind me real quick what the difference is between brackets and like the field extensions?
So this means ideal generated by h of x. We're gonna talk. We're gonna go through this and talk about what this means here in a second. Turns out you can do it, but you have to get a little bit sneaky. So do y'all remember back when I first defined field extensions? What did it mean to take a field extension of some field k?
That K is a subfield of L.
Oh, that k, some field L for which k is a subfield.
Or if you
Well,
there's
that's what
an
we said
isomorphic
it's
definition.
Yeah.
Or k has to be or some L for which k is isomorphic to some subfield. So pretty much up until now we've just been using the k just L is an extension of k if k is a subfield of L. Here's the first time we're actually going to need to go back to that original definition. Because technically Q is not a subfield of this thing. Because the elements in this are not numbers, technically they're cosets. So let's do a little bit of a recollection. Where's my here it is.
You did do some recollection on where your eraser was.
I didn't remember it. I saw it and found it. So let's call our definition. We said that L is a field extension of K. If there exists a one-to-one homomorphism phi from K to L. That was our original definition of a field extension, and this is going to be what we need to use today. Which this is the same as saying K is isomorphic to some subfield of L. Because if you just remap phi to go from K to the image of phi, that'll be onto by definition. Still be a one-to-one homomorphism, and thus would be an isomorphism to the image. Up until now, we've basically just we've only looked at the case where K is equal to a subfield of L. Technically, that is not required. And today, we'll see why that is, because it's going to help us to solve this problem of given some irreducible polynomial, how can we find a field extension and an element in said field extension for which something like that is the minimal polynomial. So Matthew, you wanted a reminder of like what does this consist of?
Yeah, well, just the difference between the brackets and like the cubex versus the like parentheses. I know the parentheses are extension.
So technically this is a set of elements right here. This is a set of all elements of the form x plus some k of x times h of x. K of x an element in n, in q of x, which is ideal in rational polynomials generated well,
Plus x.
x plus the ideal in q of x generated by h of x, yes. So basically the ideal generated by a thing is just the set of all multiples of that thing. And then having that x plus thing out in front means we just take the set of all multiples of this thing and then add x to all of them.
Is it kind of like a cyclic subgroup and then like a group?
It's sort of like a cyclic group in that you're looking at all the things that are generated by h of x. But it's a little bit different, whereas in group theory, the group generated by h of x would just be what do you get when you take h of x star itself over and over, where star is whatever your group operation is. Here it's just the set of all things that are of the form h of x times something in your ring.
Okay.
Your ring in this case being q of x. Does that make sense?
Yeah.
Yeah. Haven't done much with ideals in a while. Kind of talked a lot about them week one. And, they're coming back today to help us solve some problems. So, y'all ready for first theorem? All right, first theorem says that if k is a field and m a monic irreducible polynomial in over k, then there exists a field extension L of k and alpha an element in L for which alpha has a minimal polynomial. So if k is a field, m is a monic irreducible polynomial over k. In order to possibly be a minimal polynomial, it has to be monic, and it has to be irreducible over k. Those are kind of necessary conditions to be a minimal polynomial according to the definition. Turns out that's all you need, because then there exists a field extension. K, and alpha, element in L, for which alpha has a minimum polynomial. Has minimum polynomial. So let's see if we can prove this. I sure hope we can. Because that would be nice. That basically says anything that looks like it could potentially be a minimal polynomial, in fact, is going to be a minimal polynomial in some setting. And our proof is going to be a constructive one. We're going to specifically construct the L, we're going to specifically construct the alpha, and then we're going to show that m of x is in fact the minimal polynomial for that set alpha. Well, I need that x. This m is a polynomial. So here's what we're going to do. We're going to define L to be take the ring of polynomials over K, divide by the ideal generated by m of x. Couple questions here. First of all, how do we know that K is isomorphic to some subfield of this thing? Second of all, how do we know this thing's even a field? So, you may remember from week 1 of the semester, or last week of the semester if you had me in 410, we gave a condition under which a ring mod an ideal turns out to be a field, for R in integral domain at least.
I knew it.
Anybody remember what property I had to satisfy in order for this to happen?
It had to be max,
Yeah, if I was a maximal ideal.
maximal and,
Maximal and what?
we have maximal and minimal related.
Oh, hey,
Whoa,
couldn't possibly be any relation there.
no.
Which turns out to be the case in the case that I is generated by one element. By some element little r. Turns out that's if I is maximal if and only if r is irreducible. Say what? That's a fun thing to prove. I don't know, maybe a good question for homework 6 someday. But it turns out an irreducible element always generates a maximal ideal. Maximal ideal meaning your ideal can't, there's no ideals properly containing it other than the entire ring. And that's the case if and only if R mod I is a field. So in this case, the fact that m of x is irreducible means the ideal that it generates is going to be maximal, which means L here, this quotient ring has to be a field.
That is crazy.
If m of x wasn't irreducible, this would not be a field, and things would fall apart very quickly here. We also need to show that K is isomorphic to some subfield of this thing. So we're going to we need to sum map phi that takes in elements in K and spits out elements in L. We need some phi that does this that is a one-to-one homomorphism. Not necessarily onto. So what would be a way that we could take some element in A and map it to a coset of ideal generated by m of x here? Lincoln?
If it's in m of x, it goes to the ideal generated by m of x, it goes to 0.
If it, yeah, we want it to be the case that anything that's in the ideal generated by m of x, it goes to 0. How many elements in K are going to be in the ideal generated by m of x?
Wait.
What?
Just one.
Yeah, just 0, right? So we want 0 to be the only thing that actually gets mapped to this ideal specifically. And
You can just take A plus the ideal generated by M of X.
yeah, let's just take A plus the ideal generated by m of x. What? Simpler than you thought?
Well, it's also the alpha with H of X in there.
Oh, how about that?
Wonder how that's the same.
So, I'll leave it up to you all as an exercise to check that phi is a one-to-one homomorphism. Which isn't that hard to prove. It's essentially acts sort of like the identity function, so proving it's a homomorphism comes from that. Proving it's one-to-one involves relying on the fact that no constant elements in K are going to be in the ideal generated by m of x other than 0. So L is in fact a field extension of K. With Dorito. So we know L is at least a field that does contain, it doesn't technically contain K, but it does contain an isomorphic copy of K. Or the isomorphic copy of K is just the image of this homomorphism. So the set of all elements that form A plus, and R plus m of x. The set of all these cosets is going to be the isomorphic copy inside of L that is isomorphic to K.
And there's a whole bunch of other stuff in there probably, but.
Oh, there sure is. Like x plus the ideal generated by m of x, x squared plus the ideal generated by m of x, x squared minus x plus 3, plus something in K at least, plus the ideal generated by m of x, are going to be elements that are in L but are not of the form constant plus m of x, depending on what m of x actually is. And next thing we're going to do, we're going to let alpha now be one of these ideals, specifically the ideal form by taking x plus the ideal generated by m of x. That's going to be some element in L. It's not going to be in this set. So alpha's not in this isomorphic copy of K, because x is an indeterminate. It's not something in K. It's not an element in K. And our goal then is going to be to show that alpha has to have a minimum polynomial equal to the original m of x. So how on earth do we even show that? How do we show that this alpha has minimum polynomial m of x? The only minimal polynomials we've seen thus far are working with cases where K is actually equal to a subfield of L, and not just isomorphic to. Well, I have to be creative and use some of these properties of the minimal polynomial from Big Snazzy Big Theorem, Big Snazzy Theorem, what do we call it?
Big Snazzy Big Even Theorem.
Big Snazzy Theorem, I'm going with that. So the first thing I'm going to do is to see what happens if we take this alpha and we plug it into some function over K. And for any f of x in the field extension here, I'm curious to see what happens if we were to take f of alpha. Well, by definition, we just have some f of x. If f of x has the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a1x plus a naught. If we were to plug in alpha for x, what we would get is a sub n alpha to the n plus a sub n minus 1 alpha to the n minus 1 plus a1 alpha plus a naught. Jonah?
Why is it f of x in, why are we in K?
Well, basically, when we say that f of x is in here, we're saying that all of these coefficients are elements in K.
We're not in L right now?
Alpha is an element in L. F of x, the polynomial, takes in elements in K. We're going to be...
Wait,
Well,
f of
tech-
x takes in elements of K, but we plugged in alpha?
because in any field extension, you can always plug in elements in the extension instead. Let's take a look at what happens when we do
The
that.
coefficients of f of x are in K, but you
If
can
you
plug
said-
in anything for x.
Okay.
So let's see if we can clear up this confusion by replacing all of our alphas with the expression that's clearly an element in L, just to see what happens. Now see if anything fun happens here. Plus a sub n minus 1 times x plus ideal generated by m of x raised to the n minus 1 plus a sub 1 times x plus ideal generated by m of x plus a naught. And this Emily Rose is most certainly going to come out to an element of L. So, how do we take some coset and take it to the nth power?
Well, you just use
Like for instance, if we were to
the
take
patient on it, but
x plus an ideal I
Or the
and multiply by x plus ideal I, who remembers how coset multiplication works?
Wait, I know that there is a formula, and it's something, it's x times x plus y, right?
Yeah, you just multiply the corresponding elements together, and then add I to that.
I love it when they work how they're not supposed to.
I know, looks like something you should foil, but it is very much not the case.
Yes.
it's goofy.
That's just from, that's just how coset multiplication's defined.
I get it now. Wow.
It's crazy.
Alright, Parker, then tell me, if I take x plus ideal generated by m of x, raise that to the nth power, what are we gonna get?
You're gonna get a to the n, x to the n, plus just the ideal generated by m of x.
Bingo. And
But that's all gonna
That's the n.
factor out.
plus the ideal generated by m of x,
Yes.
plus a sub n minus 1, x to the n minus 1,
Oh wait, we're just gonna get a bunch of.
Yes. Same.
plus the ideal generated by m of x,
Holy cow.
plus a1x, plus the ideal generated by m of x, plus our a naught term. Alright, here's a question. How do we add two cosets together? I'm sorry, Isaac, but Parker looks like he's gonna explode if I don't let him answer.
That's a good point.
It's gonna be r plus s plus I.
Yeah, you just add the corresponding elements and take that coset. So what are we gonna get? Well, we're gonna get a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a1x plus what do we do with this a naught?
Just put it in,
Just put it in.
it's just part of that column.
Oh, just do it like this?
Yeah. Oh, wait.
Is that what you want to do?
I mean, that's what I wanna do.
I
I
mean,
just don't know that we can do it.
Well, technically, if we're plugging in alpha, this a naught, in order to be an element in the ring in the first place,
Is
a naught actually has to correspond to a naught plus the ideal.
yeah.
Oh.
So this actually does have one of these attached as well. Otherwise, it's not something we'd be able to add. We'd be adding apples and oranges, and that would be sad.
It's f of x plus the ideal generated by.
Oh, hey, that's just f of x plus the ideal generated by m of x.
That's kind of interesting.
It is. Yeah, and it really just comes out from the fact that coset addition and multiplication works the same way as addition and multiplication in K, or in polynomials over K, as the case may be.
That is the most convenient thing ever.
Oh, and it's certainly convenient for us here. Because what can we do with that? Well, then I claim that we know if f of alpha is equal to 0, what does that mean? Well, that's synonymous with saying f of x plus ideal generated by m is equal to the same ideal, or is equal to the same coset as 0 plus ideal generated by m. 0 being the coset corresponding to just the ideal generated by m plus 0, or the ideal itself. So what's that equivalent to saying? Well, that's equivalent to saying f of x has to be an element in
The ideal generated by
the ideal generated by x, get back there, m of x. Which is itself equivalent to saying of x divides f of x. By the way, next page is blank if you want to write on that, for those of you who've tried to squeeze this into the packets. So, So m of x is a monic irreducible polynomial that has the property that any polynomial for which you plug in alpha and get 0 satisfies that m of x has to divide that polynomial.
Wait, so when we said for any f of
I
x,
don't think we need to show that. I think we're done.
when we said for any f of x and k of x, that was specifically any f of x such that f of alpha equals 0?
Well, here, all of this computation works for any f of x and k of x.
But then when you have.
It just so happens
Then we
that,
say if f of alpha equals 0, then all of this follows.
yeah, then if this happens to be 0, if f alpha is 0, well, that means that that is 0, which means f of x is in that ideal, which is that. Do you remember back to when we proved Big Snazzy theorem and we had to prove it in like 10 parts? The first thing we did was we said like, all right, suppose that this is a monic irreducible polynomial, and then we proved this property of the minimal polynomial, and then use that to show uniqueness. Turns out that f of x being m of x being monic and irreducible, and having this property that some f of alpha equals 0 if and only if m divides f, is all that we needed in Big Snazzy theorem to show that m of x is unique, as there's only one polynomial that has all these things that we've shown so far, the minimal polynomial. So thus, by Big Snazzy theorem, since m of x has these properties, it must be the minimal polynomial of alpha. How about that? I will note that in Big Snazzy theorem we did assume K was a subfield of L because it made all the notation much easier and nicer. Big Snazzy theorem would have worked just as well though if we had assumed K was isomorphic to a subfield of L instead. It just would have been, all the same stuff but messier notation. Any questions before we move on to looking at a couple of examples? Yeah, Isaac.
Do we need that it's irreducible?
Oh, m of x better be irreducible. Otherwise, L is not a field.
Okay, but if you have
For this part, since m of x is
yeah.
to say minimal polynomial, yeah. If m of x wasn't irreducible, then if m of x is
I'm just saying you need to know that, or can you prove that once you have?
yeah. Well, technically, you can prove that as a result of this.
Yeah.
The fact that f of alpha equals 0 if and only if m of x divides f of x. M of x is required to be irreducible or it has to be irreducible in order for that to happen.
But yeah, and here we only used it to show
Yeah.
the subfield part, which we had assumed back in the proof of.
Yeah, well, yeah, we assumed m of x is irreducible so that L became a field, and if L is not a field, then if L is not a field, then all of this computation actually becomes poorly defined.
Yeah.
We couldn't do any of this basically.
It's like a different order of proof for this. big
Sure, we assumed m of x is irreducible, which means that L is how we defined it is a field, which means we can do all of this coset rigmarole. And we end up with this nice property that we never could have gotten had m of x not been irreducible in the first place. So let's look at an example. Let's go back to our good old-fashioned x squared plus 1. be, in this case, what would our L be in this case? Let's assume K equals R, for instance. Our base field is going to be R in this case. So how would we, if we wanted to use this sort of approach to find some field extension for K, in which x squared plus 1 is the minimal polynomial, Parker, what would we get?
You would want L to be equal to R over the ideal generated by x squared plus 1.
That?
No,
No?
R, the polynomial's in R.
I was gonna say that is.
Oh.
I was gonna say this is not a subset of R, so
yes.
you need that.
Okay, yes.
You know what else is a field extension of R containing some element that's a minimal polynomial of x squared plus 1?
I don't know, what is that?
Complex numbers.
Wow.
Remember what we proved week 1, week 2? First couple weeks of the class about the relationship between these two rings using, fit. What did we prove using fit?
We showed that those are isomorphic.
Oh, yeah, we proved these are isomorphic to each other. That's interesting.
It's not related at all.
It's probably not related at all. You're right. Let's do another one. How about x to the 4th minus 10x squared?
Wait, so what do we do exactly? It's just, do we just need L and K for
Say what?
this here? Do we just need L and K for this here? We don't have to find an actual M of X?
Oh, we're given the m of x. This is the m of x.
Oh, right,
It's what we're
yeah.
given to start with. Do you mean do we have to find the alpha? Is that what you're asking?
Well, yeah, but how do we need to be able to?
Yeah.
Okay, but how?
Well,
I'm missing
well
a few
here,
steps.
here alpha equals I. Here alpha is x plus ideal generated by x squared plus 1. Well, they're not equal, but it turns out that whatever isomorphism you have between these two things is going to map that to that, or that to that alpha, order you have the isomorphism structure.
They're isomorphic.
One gets mapped to the other in your isomorphism.
But other than I mean, for this one it's obvious, but if it were not obvious what alpha is.
Let's take a look-see.
I might recognize this one, but it is not immediately evident
Oh,
what
wait,
alpha
also
is.
recognize.
I'll give you a hint. We've seen this one before.
I remember this one.
It's not square root of 2.
It is not square root.
Square root of 2 has minimal polynomial like square root of 2.
Square root of 2 plus square root of 2.
Oh, well, you had an awfully long pause in there then. But yes. Turns out this thing is the minimal polynomial. For alpha equals x plus ideal generated by x to the 4th minus 10x squared plus 1. And let's say, I don't know, q of x mod ideal generated by x to the 4th minus 10x squared plus 1. It's also the minimal polynomial for alpha equals square root of 2 plus square root of 3 in what ring? Well, actually, there's a lot of fields you could put here. Let's keep it simple though, and just say q adjoins square root of 2 plus square root of 3. Get it? That was a pun. It's a simple extension.
I missed the word that you said. No, I thought it was just in Q. Because for that one,
Well, over q, yes. K here is q in both cases. But alpha here is living in two different L's. This alpha is an element in here. This alpha is an element in here. Yeah. Where
It literally means in, like, element of.
yeah, alpha, where alpha an element of this. But over K is the base field in both cases. k equals q. Oh, that's interesting. In one field, simple field extension, we got that. And another simple field extension, we got that. It's minimal polynomial for something over both of these. Turns out, I think we can define an isomorphism between these things.
That is crazy.
In fact, you can even use fit to do it. Let phi go from L1 to, or let's say from L2 to, oh gosh, I didn't prepare this, what am I doing? Q of x, phi of
We're gonna never read
a plus b times square root of 2 plus square root of 3 equals, no, not equals b of x.
8 times the ideal.
Why am I doing this to myself?
Wait, if we're trying to use fit, then we want it to go from q of x to something in q adjoin square root of 2 square root of 2.
Okay, I think we want this. No, that's not on 2.
What would be
Is that the
minus
ideal
10x
generated?
squared?
But it can't be, that's not
It
what.
can't be, because we have to go into this in order
Can
for
we
this
just
to
use
work.
Oh,
fit
yeah.
and define it as like plugging in square root of 2 plus square root of 3 into
So L2,
and then-
alright, let's think of it, yeah. So instead of just trying to write it out like that, think of this as some polynomial of alpha with coefficients coming from q. And map that to f of x. Okay, that's what we want to do. Yeah. And then that's going to be on to, and then you use fit and show that the kernel happens to be ideal generated by this thing, and it turns out you get an isomorphism. That's a fun coincidence.
It probably doesn't mean much though.
I don't know. Wonder what our next theorem will have to say. Thanks for getting ready for the sake there. So our next theorem actually makes this it's more explicit and says if you happen to have two different simple field extensions over which the same polynomial happens to be the minimal polynomial, then the simple field extensions turn out to be isomorphic to each other.
What does canonical extension mean?
I'm going to explain that.
Yeah, it's when you add books to the Bible.
It's the most. It's the mapping. It's the mapping that's the most obvious and natural one. Once you try and write out what everything means.
You include the apocryphal ones.
Don't.
Yeah, what about the apocryphal?
The apocryphal.
I mean,
The apocryphal extension.
I'm a Catholic, so.
Oh, I'm sorry, the deuterocanonical.
All right. Let's suppose. All right. Let's get into something that's definitely a lot less technical than all that. Let's let B from K to K prime be an isomorphism of fields. With canonical extension, and yes, I'll define what that means here in a second. Something that shows up a lot now, but it doesn't mean that. It just means do the obvious thing. To K prime of x. Alright, let's write this down over to the side so you will stop. I get all religious on.
We're in Hillsdale.
We are in Hillsdale, but you know, shut up.
The applied math book did a study about this too.
Alright, so we have some map T that takes in elements in K and spits out elements in K prime. And we want to somehow come up with a new map, phi, that takes in a polynomial here. And spits out some polynomial in K prime. So, how how can we somehow use phi to take in a polynomial here, where this thing is in k of x, and somehow spits out a new polynomial whose coefficients are in k prime? What's the most natural way to do it? Jonah?
Would be phi alpha, or a, sorry, if a and.
Yeah, you literally just plug in all the coefficients into phi. Kind of do the thing that's hopefully the most obvious for thinking about how would you take a polynomial over k to a polynomial over k prime. You just map the coefficients of the k polynomial to their corresponding elements in k prime using your map phi. So that's what we mean by the canonical extension, Emily Rose, is given any time we have some sort of homomorphism from k to k prime, we can use that to create a new homomorphism from polynomials over k to polynomials over k prime in this way. Does that make sense? Cool. All right, let's finish actually writing this theorem down. So we're going to let phi be a field isomorphism. There's our canonical extension. We're going to let f of x be some polynomial that's irreducible over k. Next thing we're going to do is we're going to define two different field extensions. We're going to let L be an extension of k containing a root of f, which we'll call alpha. And we're going to let L prime be an extension of k prime containing a root alpha prime of f. So we're basically doing two different field extensions. One is going to be a field extension of the original field k, that's going to have a root of f. This should say, sorry, f prime, which we're defining to be phi hat applied to f. Where in other words, we've just taken all the coefficients in f of x and we've replaced them with whatever the coefficients that phi in k prime that phi maps them to. So we're just taking.
Just put hats over everything instead of having some things prime and some things hat.
It's a party. Party.
But they're doing different things. Well, then it turns out that there exists a ring isomorphism psi from k of alpha to k prime of alpha prime.
Are those square brackets or parentheses?
Oh gosh, are those square brackets or parentheses?
Wait,
Oh gosh,
it doesn't matter.
it's equal by the big snazzy theorem.
Yes.
So go with whichever one you
Yeah,
prefer
or
in
the
this
nice
case.
Whichever one you
Such that two things happen. First of all, alpha gets mapped to alpha prime, and for all elements in k, they get mapped to whatever phi would map them to. Psi of b is just going to be the same as phi of b. Whew! That's a big theorem. There's a lot of pieces to this theorem. But to sum up, what it really means is if you make two different simple field extensions that use the same minimal polynomial, then the simple field extensions themselves are going to be isomorphic. Even if the base field k and k prime aren't equal to begin with, but are just isomorphic to each other. So let's write this down before we try and prove this. How are we doing on time? Oh, we're good. So good.
It still feels like it should be the end of class now to you.
Say what?
It still feels like it should be the end of class now to you.
Well, I just didn't. Shut up. Which really what this is saying is if k is isomorphic to k prime via some map phi, and two different field extensions are made, two different simple, I should say, field extensions are made using roots of the same minimal polynomial. Then the extensions will also be isomorphic. If k and k prime happens to be the same field, we'll see as a corollary after we prove this, then we're essentially just saying k of alpha is isomorphic to k of alpha prime. If we extend by out one root of the minimal polynomial alpha as opposed to another root having the same minimal polynomial. Any questions or comments about that before we try and start proving this thing? This theorem looks big and scary. It's not actually as hard to prove as you might think. It does involve some amount of work, but not as much work as, say, big snazzy theorem did. So let's start with proof. Wapow. So the first thing we're going to do is we're going to note what k of alpha consists of. Given an extension like this, well, k of alpha by definition is going to be the set of all polynomials of the form a naught plus a1 alpha plus a sub n minus 1 alpha to the n minus 1, where the a sub I are all elements in k, where n is equal to the degree of f. F here being the corresponding minimal polynomial. Technically, f doesn't have to be the minimal polynomial. It just has to be an irreducible polynomial containing alpha as a root. It doesn't have to be monic. But then you're just looking at a unit multiple of the minimal polynomial anyway, so it's a basic idea. So kind of by definition of how these field extensions work, all elements in here are going to consist of polynomials of alpha, where alpha to the n, we don't need alpha to the n and beyond terms because alpha is satisfying some polynomial of degree n, is a root of a polynomial of degree n. So alpha to the n could be written as a linear combination of these things. Sound good? So now we're going to define our psi here. We're going to define psi to be a map from k of alpha to k prime of alpha prime. And the way we're going to define that is psi is going to take in one of these polynomials, a naught plus a1 alpha plus a sub n minus 1 alpha to the n minus 1. And what it's going to do is all of the alphas are going to get replaced with alpha primes, and all of the a sub I are getting replaced with phi of a sub I. So a naught goes to phi of a naught. A1 goes to phi of a1. Alpha goes to alpha prime.
And alpha prime is just another root of f.
Just a second. Should. Alpha prime here is just another root of the same minimal polynomial. Technically not the same minimal polynomial, but the isomorphic copy of it over k prime.
Okay, cool.
So alpha prime is a root of phi hat of f. So the a sub I So the coefficients in k are being turned into coefficients in k prime. The alphas are becoming elements in alpha prime. And I claim this map is an isomorphism.
Writing alpha prime to the n minus 1 is difficult.
Oh yeah, this should be a prime.
My point is made.
Oh no, I just forgot to do it. Here, let's do that. It's not that, I just put it in parentheses.
Yeah.
And now it's bleeding into the office hours. There.
Just plug everything all with.
No, we're not using that notation. Don't be ridiculous.
We should use that notation though.
Shut up.
Just for clarity.
So basically, what we need to do is we need to show that psi is an isomorphism. So how do we show something's an isomorphism? We need that it's a homomorphism with respect to addition and multiplication. So there's two things we need to do.
And it's onto and 1 to 1.
And that it's onto, and that it's 1 to 1.
Or we can make it an inverse and then it's onto and 1 to 1.
Or we could do that. Which actually works just as well here. The fact that it has an inverse comes from the fact that phi has an inverse, essentially. Why? Because phi is not. The fact that phi itself is an isomorphism from k to k prime is going to be super helpful in helping us determine that. So let's start with psi 1 to 1. This is probably I think this one's the hardest of the things we need to show, so start off with the tricky so we can move towards the simple. So let's suppose we have some psi of, oh, I just realized I don't like my notation choice. I need some F and some G. Let's say psi of G of alpha equals psi of H of alpha for some G of alpha equals, we'll call it A naught plus A sub 1 alpha plus A sub n minus 1 alpha to the n minus 1. H of alpha will be B naught plus B1 alpha plus B sub n minus 1 alpha to the n minus 1. I've been saying all morning because I had something similar in 105 that I was and it's been fun. These things, elements, the coefficients coming from k. So in the simple extension k of alpha. And our goal is to prove that G and H are in fact exactly the same, that all of their coefficients match up perfectly in order to prove one-to-oneness of this side. Well, we set these equal, then we get psi of A naught plus A1 alpha plus A sub n minus 1 alpha to the n minus 1 equals psi of B naught plus B1 alpha plus B sub n minus 1 alpha to the n minus 1, which we've actually plugged those things into our map psi. We're going to get phi of A naught plus phi of A1 alpha prime plus phi of A sub n minus 1 alpha prime to the n minus 1 is equal to phi of B naught plus phi of B1 alpha prime plus plus phi of B sub n minus 1 alpha prime to the n minus 1.
It's really fun to say.
It is, isn't it? Emily Rose, are you unhappy?
No, I don't think I am. I was trying to remind myself why the B's are all the same, because
Why what B's?
okay, so you apply phi to the whole thing. Okay, never mind.
We're applying psi to the
Psi
whole
to
thing,
and
which
then,
means using phi here.
which means using phi on the coefficients, which gives you phi of phi of all the A's and phi of all the B's.
So we're going to subtract everything from both sides and combine the same powers of alpha together. So that's going to give us phi of A naught minus phi of B naught plus phi of A1 minus phi of B1 all of that times alpha prime plus burp 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 plus phi of a sub n minus 1 minus phi of b sub n minus 1. All of that times alpha prime to the n minus 1 can equal 0. Well, phi's an isomorphism, but we're not quite ready for that yet. Here's my question. What do we know about the relationship between alpha prime squared, up to alpha prime to the n minus 1?
They're linearly independent,
They're linearly independent.
so it can't.
That's something we've seen kind of several times working with the minimal polynomial, that powers of alpha up to 1 less than the degree of the minimal polynomial are linearly independent of each other, which means
That the only solution for which all of those equal 0 is if all of the coefficients are equal to 0.
exactly. So this has to equal 0, this has to equal 0, and this has to equal 0, which tells us by the linear independence of the alpha prime powers, of the powers invested in me as an alpha prime, for each I, phi of a sub I minus phi of the corresponding b sub I is equal to 0, which in turn tells us phi of each a sub I is equal to phi of each corresponding b sub I. And what do we know about phi that's going to be helpful here? As an phi's an isomorphism, so it has lots of nice properties. But in particular,
If phi of a sub I equals phi of b sub I, then a sub I equals
because phi is,
1 to 1.
1.
well, it's an isomorphism and therefore is 1 to 1.
All of the words that we said are true.
You're right.
They all true.
Some of them
One follows from the other, but they're all true.
And then from here, the fact that all the coefficients are the same is going to tell us that our original g of alpha has to be equal to h of alpha. Because a naught equals b naught, a1 equals b1, a sub n minus 1 equals b sub n minus 1. Oh, excuse me, plus a sub n minus 1 equals b sub n minus 1.
Now,
I saved so much space by just writing all of that in summation.
Look, aren't you special? Yeah, if it was any longer, I would have used summation too.
but if you use summation, you can't say burp burp burp.
I don't want to say burp burp burp, and
Well,
burp
then
burp
you-
burp takes up a lot of my
or-
page.
Oh, come on, don't tell me you didn't have fun saying burp burp burp
This
just now.
letter is called burp, burp, burp.
Oh yeah, sigma is called burp burp
Oh
burp.
gosh, what did I do?
I don't know what a sigma is, but.
Alright, so we know psi is 1 to 1 at the very least. Actually, let's
use this guy.
So we still need that psi is onto and a homomorphism.
Confusing, no, probably
I'm gonna leave onto up to you all as an exercise.
Leave it out to us.
Appropriate note. Seamus, your laugh gets creepier every time I hear it.
Makes me want to stay further.
So,
That's a better laugh. Yeah.
and the fact that psi is onto is actually pretty straightforward. It really just comes from the fact that phi is onto relatively quickly. You have some polynomial of alpha prime. Use the fact that all the coefficients of that polynomial in k prime have to get mapped to by some coefficient from k, and psi of whatever corresponding polynomial you get over k of alpha maps to that k prime and alpha prime polynomial. So the last thing we need to do is a homomorphism, which one part of homomorphism is easy, one part is less so. Turns out the addition part, pretty straightforward. I'll leave it to you all to check that psi of f of alpha plus, or g of alpha plus h of alpha is equal to psi of g of alpha plus psi of h of alpha. And then multiplication is a bit messier. So let's do that one as a class. And for proving that this is a homomorphism with respect to multiplication, we're actually going to use the Euclidean algorithm. The old standby. I want to stick around for a couple minutes after class because this will take about 5-6 minutes to do.
I won't die.
Alright, let's do it. Alright, we're going to write out then some f of x times g of x, or g of x times h of x. Oh gosh, I'm already screwing up because I realized I butchered my notation again. I used f of x for something I shouldn't. So we're going to take some g of x and h of x, and we want to show that psi of gh equals psi of g times psi of h. We're going to take the product of g and h and write it as being equal to q of x, m of x, or q of x, oh that's why I messed this up, f of x. Remember, f of x is the thing that we said was the irreducible polynomial early on. Plus some r of x with the degree of r less than the degree of f. And if we do that, then we can take psi of f of alpha times g of alpha. That g times h. A classic Dr. Gerstle tries to redo all of his notation on the fly and flubs it horribly. Well, by definition, that's just going to be psi of q of alpha times f of alpha plus r of alpha. Oop, that's you're supposed to be an alpha. What's alpha of alpha?
0.
Hey, alpha is defined to be a root of this thing, so that's 0. So we just get psi of r of alpha, which by definition is, hold on to your hats, phi hat of r applied to alpha. Or remember, r is just some polynomial, and plugging r into phi hat just takes all the coefficients in r and applies phi to each of them to make them coefficients in k prime instead.
What is-
Yes. Which in turn equals phi hat of q of alpha prime times phi hat of f of alpha prime, plus phi hat of r of alpha prime. Why? Because this is 0.
Okay.
Because f alpha prime is defined to be a root of f hat of f prime, which is the same as phi hat of f. Which in turn is the same as writing this as phi hat of q, phi hat of f, plus phi hat of r, and applied to alpha prime. Which is the same as phi hat of g times phi hat of h. All that applied to alpha prime, which is the same as phi hat of g of alpha prime times phi hat of h of alpha prime, which is the same as psi of g of alpha prime. Psi of g of alpha, yes, you're right, times psi of h of alpha. And so, notation gets messy, but the moral of the story is psi of g times h is equal to psi of g times psi of h. And thus we get a multiplicative homomorphism, and thus psi is an isomorphism, and thus we have completed our proof of the new big snazzy theorem of the packet. Hope y'all have a good one. See y'all on Tuesday. So on Tuesday we'll look at a corollary, the simpler version of this, where k and k prime are the same base field. In which case the notation just gets a lot nicer, but it says essentially the same thing. And then we'll look at some examples and go on from there to talk about what happens if instead of just given some irreducible f of x, instead of extending to having an extension where you have one root of your polynomial, what if you have extend to get many roots? You'll get something called a splitting field. Talk about it on Tuesday. End the video.